Video. Video on a cassette. Pretty cool, right? This is a composite video cable. It sends analog video over a single wire. And this is a stereo RCA audio cable. It sends analog audio over, well, 2 wires. Do you notice something? They got the same kind of plug on them. Have you ever wondered what would happen if you were to just, cross the streams? Well, not much, actually. While we can definitely record a composite signal onto a cassette, or plug this into an audio interface to record it onto a computer, the bandwidth of a composite video signal is way too high to be accurately recorded by equipment meant for audio signals. What do I mean by that? Well, let's do a calculation. The resolution of a standard definition PAL video is, in a very simplified and hand-wavy kind of way, around 768 by 576 pixels at 25 frames per second. That's a total of just over 11 million pixels per second. So if all those pixels are completely different, we would need to store 11 million different values, or samples per second, to accurately record that signal. That's a lot of data. And that's assuming we're only storing a single value for each pixel, like the brightness. So there's no color here. This is just a black and white image. Let's compare that to a cassette recorder like this, or an audio interface like this, which are meant to store signals in the range of human hearing, usually up to around 20 kHz. To do that digitally, according to the Nyquist-Shannon sampling theorem, we're going to need twice the amount of samples per second than the highest frequency we want to record. That's why digital audio on a computer usually uses 44.1 or 48 kHz sampling rate, that is, it stores 44,100 or 48,000 values per second to record the signal. It allows you to comfortably capture and play back frequencies up to 20 kHz and a little above. Now, what's the frequency of our video signal? Using the Nyquist-Shannon sampling theorem in reverse, we know that 11 million different samples or values per second can result in a frequency of up to 6.5 MHz. And if you look up the actual bandwidth of a composite video signal, you're going to see that even with our hand-wavy calculation, we're pretty close to the actual value of roughly 5 MHz. And that's a problem. 5 million is a bigger number than 20,000. And I guess the reason I went through all the trouble of inventing the VCR. So we're gonna have to make some changes, and the easiest change to make is to reduce either the resolution or the frame rate of the video to reduce the amount of data we need to store. And actually, we probably need to do both. 100 by 75 pixels at 5 frames per second. That's what I came up with. And that's what that looks like. It's not a lot. And if you want widescreen, you're gonna have to stretch it a little. But it's gonna fit onto a cassette. So, how do you actually do this? How do you turn a video file into sound to put onto a cassette and then play it back later? Well, with Python and JavaScript, of course, and a tiny bit of magic. Let me see if I can explain the whole process without bringing out a whole bunch of pieces of paper with code on them. Let's keep it simple and pretend we're only trying to send a single picture. This one, in fact. The first thing we need to do is split up our picture into a number of lines, equal to the vertical resolution we want. To keep this manageable, let's say that resolution is 7 lines. Yeah, I actually used this thing. The next thing we need to do is to turn this into some kind of audio waveform. And the easiest way to accomplish this is to just use high values for bright pixels and low values for dark pixels. So for the first line, we might get a waveform that looks something like this. Yeah, that's just a line. That's not very interesting. Let's do the second one. That's a little bit more interesting. We can see waveforms mostly down there, and then we got 2 humps for the 2 white pixels. Let's keep going with that for the rest of the image. But now we have a problem, and not just that I didn't plan this correctly and this doesn't actually fit on screen. The actual problem is, if we were to just take all those waveforms for each line and stick them end to end into one big waveform, we don't really have a way to tell where one line ends and the next one begins. These pieces of paper are just kind of a metaphor after all. You might think, can't we just measure the time? We know how long each line is after all. Well, yeah, but no. Imagine turning your TV on in the middle of a broadcast. How are we going to know where to start our image, or each line of the image? Also, once this is playing back from an actual cassette, it's going to be very hard to actually keep the decoder in sync with the always slightly varying speed of the tape. Luckily, we can just take a look at how they did it in composite video and kind of steal their idea. Synchronization pulses. If we introduce a short pulse between each line, that is outside of the range where the actual signal can go, it's pretty easy to pick that signal out and use it to synchronize our receiver. And by making the pulse that starts the first line different than all the others, we know when a new frame starts. Composite video actually uses long and short pulses instead of pulses that go high-low or low-high. If you're curious why I did that, it's got something to do with not introducing too much DC bias into the signal, and if you're not curious, that's fine too. And here we go. An audio waveform that represents our initial picture with enough additional information to actually allow us to get the image back. We can now write a small program that takes a series of images as input and creates a sound file containing the generated signal as output, which is exactly what I did. But wait, you say, this has color, and it's faster than 5 frames per second, and there's audio. Well, you're right. I lied. Let me explain. My final version of this actually uses interlacing. We double our frame rate, but for each frame we only send half the lines. On even frames we send the even lines, and on odd frames we send the odd lines. This trades off a little bit of weirdness in the image where the frames don't quite match up, for a lot less flicker. Color is a little bit more complicated. Composite video uses a pretty complicated technique to modulate the color signal onto the black and white signal for reasons of backwards compatibility with black and white televisions. But we actually have a whole nother audio channel here that we're not using yet. Of course, to transmit color in RGB, we would need 3 channels instead of the 2 we have. But we can cheat a little. There's actually a color space called YCBCR, which splits up the image into 1 brightness and 2 color channels. That means we can store the brightness in one audio channel and use the other channel to send the 2 color components on alternating lines, or just repeating the other color from the previous line. That means we're cutting the color resolution in half, but at this point, who's counting? Oh, and the audio? It's fake. I just recorded with the Salt Dictaphone brand dictaphone. No, there isn't. Sorry. Though if you opt out of color, you could probably use the second audio channel for mono audio. And that's how it works. Video on cassettes. Of course, there's a lot of stuff we can tweak here. While there are some pretty severe limitations in terms of bandwidth, you can of course choose how to spend that bandwidth. You could reduce the frame rate to get a higher resolution, or change the resolution in one direction to increase it in the other. If we, for example, lower the frame rate to 4 frames per second, we'll get a whole 150 lines of resolution and a much sharper and less glitchy image overall. But where's the fun in that? Actually, there's a lot of fun in that. I released an EP of my music in 2018, which had a time-lapse of a single day passing in front of my window on its B-side, playing at a leisurely 2.5 frames per second. Link to the video and music down in the description. And that's it, I think. There's a link to the code with some documentation in the description below if you want to make your own videos to put onto cassettes. The encoder is a small Python script, and the decoder is written in JavaScript, so you can easily embed it into a website. I'm fully aware I had to gloss over quite a few details here for the sake of actually finishing the video. So if you have any questions, just leave a comment and I'll gladly answer them. Okay, that's it. Take care, everyone.